the chemical crucible, grade 150 fuel, and the industrial triumph in the air war. Early 1944. The icy wind swept across the open field at Wright Field, Dayton, Ohio, carrying the metallic scent of fuel and the steady thrum of machinery that never seemed to rest. On the tarmac, a silver P-51 Mustang gleamed beneath the pale winter sun, its long fuselage stretching like a predatory arrow toward the horizon. Inside the cockpit, a test pilot adjusted his oxygen mask and steadied a gloved hand on the throttle. He knew this flight would push his aircraft, and his courage, far beyond any officially sanctioned limit. The Packard-built Merlin engine growled, then roared as the throttle advanced past the familiar war emergency power settings. The manifold pressure gauge climbed relentlessly, past 70 inches of mercury, towards 75. The sound deepened, transforming into a ferocious, sustained scream as if the engine itself were breaking through an invisible barrier. What powered it was no ordinary fuel. It was something new, experimental, and strangely beautiful, a liquid dyed a vivid, triumphant purple. Its name was grade 150. The Mustang leapt forward. The airspeed indicator swept past 400 miles per hour and kept climbing. At 25,000 feet, the aircraft reached 448 miles per hour, slicing through the thin air faster than any production fighter had before. In the control tower, engineers exchanged nervous glances. They were witnessing the birth of something extraordinary, a chemical revolution contained within a gallon of gasoline. This was not just another test flight, it was the moment when chemistry, engineering, and industry converged to redefine the limits of aerial warfare. Up to that point, air combat had been measured by aircraft design, engine displacement, or pilot skill. But on this cold Ohio morning, those metrics were being rewritten. The United States had unlocked an advantage so profound that it would change the very balance of the air war over Europe. The weapon was not a new airframe or secret supercharger. It was the invisible chemistry within the fuel tanks, fuel that could coax unimaginable power from existing engines, turning established performance boundaries into mere suggestions. The science behind this transformation lay in an obscure but decisive property: detonation resistance. Every internal combustion engine relies on a delicate balance between compression, heat, and controlled ignition. When that balance tips, when fuel ignites prematurely, the result is detonation, a violent and destructive shock that can destroy an engine in seconds. To resist detonation, fuel must have what chemists call a high-octane rating, or, more precisely for aviation, a high-performance number. During the 1930s, aircraft designers across the world chased higher and higher octane ratings. Each gain meant an engine could run at greater compression, yielding more power without self-destruction. By 1939, the Allies had standardized 100-octane aviation gasoline, while most of the world still relied on 87-octane blends. This seemingly technical distinction already gave British and American fighters a measurable edge during the early years of the war. But by 1943, the race had intensified beyond imagination. In Germany, resource scarcity forced the Luftwaffe to rely on synthetic fuels produced from coal using the Bergius process. These fuels, though technically sophisticated, suffered from inherent chemical limitations. Their detonation resistance capped at the equivalent of about 91 octane for standard B4 fuel, with the higher grade C3 fuel barely matching Allied 130 grade performance. Meanwhile, in the laboratories of Standard Oil, Shell, and Anglo-Iranian, American and British chemists were quietly breaking the theoretical ceiling. They achieved something remarkable: a fuel with a performance number of 150. That figure did not mean it contained more octane, in the literal sense. Instead, it represented the level of compression pressure the fuel could endure compared to pure isooctane. At rich mixture settings, this new formulation tolerated roughly 50% more load before detonation occurred. In practical terms, it allowed engines to operate at unprecedented manifold pressures, safely extracting hundreds of additional horsepower without redesigning the engine itself. When test pilots first ran the Merlin on this purple fuel, they knew instantly that they were handling something transformative. The boost gauge told part of the story, but the rest could be felt through the stick. The surge of acceleration, the responsiveness, the way the Mustang seemed to shrug off aerodynamic drag. The difference was not incremental, it was existential. For the Luftwaffe, the implications were catastrophic. At altitude, a Messerschmitt Bf 109G could reach about 400 miles per hour. The newer Focke-Wulf FW190A might touch 408. Against Mustangs running ordinary 130 grade fuel, these figures kept the contest uncertain. Skill, altitude advantage, and surprise still mattered. But when the same Mustangs switched to 150 grade, the fight became unequal. With a 40 to 50 mile per hour speed advantage, American pilots could dictate every engagement, choosing when to fight, when to disengage, and when to climb away untouched. The Germans were trapped in an equation that no amount. Years earlier, during the anxious months of 1940, General James Doolittle had already seen where the future lay. Even before America's formal entry into the war, he argued that high-octane fuel would be the critical determinant of air superiority. His advocacy convinced both the Army Air Corps and the major oil companies to invest heavily in advanced refining technology. Among the key contributors was the French-born engineer Eugene Houdry, whose pioneering work in catalytic cracking allowed crude oil to be separated and transformed with unprecedented efficiency. By the time the United States joined the conflict, the infrastructure for large-scale high-octane fuel production already existed. By 1943, 17 major Allied refineries were producing aviation gasoline of exceptional quality. They were strategically located in the American heartland: Detroit, Pittsburgh, Chicago, far beyond the reach of Axis bombers. Operating day and night, these facilities represented the purest expression of industrial warfare, safe from attack, well supplied, and constantly improving. The contrast with Germany could not have been starker. The Reich depended on a handful of vulnerable synthetic fuel plants, each one a lifeline. When Allied bombers turned their attention to these facilities in 1944, the results were devastating. Raids on Luna, Merseburg, and other synthetic centers crippled production almost overnight. By the autumn of that year, the Luftwaffe faced not only a shortage of aircraft and trained pilots, but a literal absence of the fuel required to fly. While German chemists scrambled to stretch dwindling reserves, the Americans faced the opposite problem: abundance. Their refineries produced millions of gallons each month, enough to sustain thousand-plane bomber raids and the expanding escort fighter fleets that protected them. The logistical challenge shifted from production to delivery, ensuring that every airfield in Britain and continental Europe had access to the new purple fuel. When the first shipments arrived in England in early 1944, ground crews noticed the distinctive color immediately. It was more than a dye, it was a symbol of industrial victory, an emblem of the unseen laboratories and refineries that stood behind every combat sortie. In May, selected squadrons of the 8th Air Force began using the fuel operationally. The timing could not have been more significant. Within weeks, the Allies would launch Operation Overlord. For the pilots, the change demanded respect. Grade 150 fuel unlocked immense power, but it also introduced new challenges. Operating the Merlin at 75 inches of manifold pressure consumed fuel at a ferocious rate. Long-range escort missions to Berlin already pressed the limits of the Mustang's endurance, and now, fuel management became an art form. Pilots learned to hold back the throttle until the crucial moment of combat, when the extra horsepower could mean survival. That momentary burst, just a few minutes of unleashed power, could decide an entire engagement. Those who experienced it described a sensation of effortless acceleration, as though the aircraft had suddenly shed its weight. The added 250 horsepower translated not only into speed but into authority in the vertical. In a dogfight, altitude is life, and with grade 150 fuel, the Mustang could climb faster, dive longer, and recover more quickly than any opponent it met. As this new advantage spread across Allied air units, its impact rippled through the entire air war. In the skies above England, where the Luftwaffe's V-1 flying bombs began to terrorize civilian populations, speed became the essential defensive weapon. The pilot of a Hawker Tempest or Spitfire Mk-14 needed to intercept AV-1 traveling roughly 400 miles per hour. With standard fuel, the margin was perilously thin. With grade 150, the same aircraft could close the gap and destroy the target before it reached its destination. Between June and September 1944, RAF Tempest squadrons powered by the purple fuel destroyed hundreds of these weapons in midair. Meanwhile, over Normandy, the new fuel contributed to an outcome that remains one of the defining moments of the air war. On D-Day itself, only 2 German aircraft appeared over the beaches. Allied air superiority was so complete, so uncontested, that ground troops advanced under an almost tranquil sky. The invisible chemistry in the tanks of P-51 Mustangs, Spitfires, and Thunderbolts had ensured that dominance. For German pilots, the shock was profound. Reports filtered back to Luftwaffe intelligence describing American fighters that seemed immune to pursuit. Pilots claimed they could not close the distance, no matter how aggressive their throttle. At first, these accounts were dismissed as exaggerations or combat stress. It seemed impossible that existing Allied fighters had gained such speed without an entirely new engine. Only later, when German scientists examined captured fuel samples from downed aircraft and discarded drop tanks, did the truth emerge. But by then, the damage was irreversible. The psychological impact alone was immense. To confront an opponent whose aircraft could always dictate the terms of battle was demoralizing in the extreme. Experienced German aces like Gunther Rall, who had survived hundreds of sorties on the Eastern Front, now found themselves fighting an enemy that defied all familiar metrics. The Mustang's speed and climb performance left no room for error. Escape became nearly impossible. The mounting disparity between American and German performance in the air was more than a tactical gap. It was an unfolding collapse of an entire strategic worldview. The Luftwaffe had entered the war as the world's most modern air force, its doctrines built on rapid offense, precision coordination, and technological superiority. But by 1944, that foundation had eroded. Each combat report told the same story: the enemy's aircraft accelerated faster, climbed steeper, and seemed to possess endless reserves of power. German pilots who once relied on their own speed advantage now found themselves on the defensive. The Bf 109G, once a terror over Europe, could no longer dictate terms. Even the highly regarded FW-190A, prized for its roll rate and ruggedness, could not outrun pursuit. Engagements that began on equal terms turned rapidly fatal. For the first time, Luftwaffe commanders began to see entire squadrons annihilated within minutes, the familiar pattern of energy fighting replaced by one-sided slaughters in the thin air over Germany. Beneath this aerial defeat lay an industrial truth that Germany could neither match nor ignore. The Reich had built its war machine on precision craftsmanship, superb designs, finely tuned engines, and a culture of engineering perfection. But precision could not replace scale. The United States had turned industrial output itself into a weapon, transforming chemistry, metallurgy, and logistics into extensions of strategy. Every gallon of 150-grade fuel represented not only chemical sophistication but the functioning of a vast, coordinated system: refineries, pipelines, tankers, and railroads stretching from Texas to the British Isles. At the core of this system stood the catalytic cracking plants conceived by Eugene Houdry and refined by American engineers. Their continuous flow reactors broke heavy hydrocarbons into lighter, high-octane molecules with extraordinary efficiency. While German chemists struggled to coax aviation fuel from coal, each American plant was producing tens of thousands of barrels per day. The difference in productivity was absolute. In 1944, when Allied bombers targeted Germany's synthetic fuel plants, the Luftwaffe's nightmare materialized overnight. The raids on Luna, Brux, and Politz reduced production to a fraction of its former capacity. Storage tanks burned for days, pipelines lay in twisted heaps. Repair crews worked under constant attack, and even when the machinery was restored, the supply chain to frontline airfields remained broken. Fighter wings received only a fraction of their allocations. Training units were grounded entirely. fuel scarcity bred desperation. Experienced squadrons hoarded what little remained, and new pilots, barely trained, barely armed, were rushed to the front. Many of them had fewer than 20 hours of flight experience when they faced the seasoned American formations streaming across the Reich. Without fuel for extended training, they learned tactics in combat, often for only a few minutes before being shot down. Meanwhile, American pilots were flying almost daily, logging hundreds of hours in the air. They practiced formation maneuvers, fuel management, and combat drills over friendly territory before facing the enemy. The contrast in experience and confidence widened as quickly as the technological gap. As the Allies advanced toward Germany, the logistical miracle continued. Enormous fuel convoys moved through British ports, overland pipelines carried the purple gasoline to forward bases, and engineers built portable refineries to ensure continuous supply. The chemical crucible, Grade 150 fuel, and the industrial triumph in the air war. Early 1944, Wright Field, Dayton, Ohio. A test pilot steadied his gloved hand on the throttle of the P-51 Mustang, the sleek profile of the fighter silhouetted against the pale winter light. He was preparing to push the aircraft far beyond its certified operating limits, beyond the standard war emergency power settings that the Luftwaffe had learned to dread. As he advanced the throttle, the massive Packard-built Merlin engine roared, intake boost pressure climbing rapidly past the 70 inches of mercury mark towards an unprecedented 75 inches, fed by a potent, experimental fuel dyed a distinct, triumphant purple, Grade 150. The airspeed indicator swept past 400 miles per hour and accelerated towards numbers that represented the absolute edge of Allied fighter performance. At 25,000 feet, the Mustang was not merely cruising. It was surging through 448 miles per hour. In the control tower, test engineers, hands tight on their headphones, exchanged glances. This was not a modest, incremental gain. This was a chemical revolution contained within a gallon of gasoline, an industrial advantage so profound it would instantly render obsolete every defensive and offensive calculation the German Luftwaffe held regarding American fighter capabilities. The war in Europe was about to pivot, and the catalyst was not a new airframe or a brilliant tactical doctrine, but fuel that allowed existing aircraft to perform at levels that defied German technological and industrial expectations. The science of detonation resistance, the octane war. The true measure of a fighter engine's potential is the quality of its fuel, defined by its resistance to detonation, the uncontrolled explosion of the air-fuel mixture under the extreme pressure and heat of the compression stroke. By late 1944, Allied superiority was so overwhelming that entire missions went unopposed. Bomber crews reported reaching targets deep inside Germany without encountering a single interceptor. The Luftwaffe still existed on paper, but its aircraft sat idle for lack of fuel, its pilots dispersed or captured. The few operational jets, like the Me-262, offered flashes of hope but no salvation. Each required specialized fuel blends that were even scarcer than the standard stocks. Many were destroyed on the ground before they could ever fight. As defeat loomed, even Hermann Göring, once the proud architect of the Luftwaffe, could no longer deny reality. Watching contrails of American Mustangs streaking over Berlin, he famously remarked that when he saw P-51s above the capital, he knew the war was lost. It was not simply the presence of the aircraft but what they represented, an enemy whose industrial machine could outproduce, out-engineer, and outfuel the Reich. Behind that visible domination lay the silent triumph of logistics. Each Mustang over Berlin carried within its wings the labor of chemists, refinery workers, rail operators, and dock hands. The bright purple fuel that filled its tanks symbolized the coordination of an entire economy focused on victory. No single pilot, no matter how skilled, could stand against that collective momentum. The final months of the air war were a study in asymmetry. Allied losses declined even as sortie numbers rose. American pilots engaged fewer opponents, often finding empty skies where enemy interceptors had once swarmed. The Luftwaffe's last reserves of high-grade fuel were allocated to desperate counteroffensives or withheld for the defense of the homeland, but the effort was futile. Without sufficient quantities, even the most advanced fighters could not sustain combat readiness. As 1945 dawned, the evidence of collapse was everywhere. Captured airfields revealed aircraft parked wingtip to wingtip, their tanks dry, their engines cold. In hangars, mechanics dismantled planes for spare parts, while Allied reconnaissance cameras recorded the eerie stillness. On the front lines, American pilots flew low over these abandoned bases, astonished at the absence of opposition. The transformation had taken less than a year. From the introduction of grade 150 fuel in early 1944 to the virtual extinction of German air resistance in early 1945, the pace of change was breathtaking. It demonstrated how industrial adaptation could alter the course of war more decisively than any single battle. The significance extended beyond immediate victory. The success of the 150 grade program proved that chemistry itself had become a strategic domain. Wars would no longer be won solely by the number of divisions or the caliber of guns, but by mastery of molecular structures and production processes. The laboratory had joined the battlefield. When historians later examined the campaign, they found that the 448 mph achieved during that test flight in Dayton was more than a technical milestone. It was a symbol of civilization's new relationship with industry. The United States had turned fuel into strategy, blending scientific research with mass production until the two were indistinguishable. Every gallon of purple gasoline represented not just energy but organized intelligence, the coordinated effort of thousands of minds and machines. By March 1945, Allied air supremacy was absolute. The skies above Germany were no longer contested spaces but highways of bombardment and reconnaissance. The few remaining Luftwaffe fighters that dared to rise were swiftly destroyed. For bomber crews, missions that once required nerves of steel became routine exercises. The outcome of the air war was no longer in doubt. When victory finally came in May, it was sealed not only by the courage of the pilots, but by the unseen chemistry that had powered them. The story of grade 150 fuel stands as one of the clearest examples of how industrial science can determine the fate of nations. It was a triumph not of secret weapons or superhuman feats, but of systematic innovation, an invisible revolution waged in refineries, laboratories, and assembly lines. In the end, the Allied victory in the air was an equation of numbers and molecules. Germany could design brilliant machines, but America could build and fuel them in limitless quantity. The purple-dyed gasoline that coursed through the Merlin engines of the P-51 was more than a product. It was proof that the modern world's true battlefield lay within the chemical crucible. By late 1944, the contrast between Allied and Axis fuel technology had become impossible to ignore. Luftwaffe intelligence reports captured after the war reveal a growing sense of alarm among German aviation engineers. They could clearly see that the Allies were no longer winning the air war just with numbers, they were winning it with chemistry. The Germans had built extraordinary engines, the Daimler-Benz DB605, the Junkers Jumo 213, the BMW 801, marvels of mechanical engineering. But they were shackled by fuel quality. Their C3, aviation gasoline, though respectable by 1941 standards, topped out around 96 to 100 octane. Attempts to blend higher grades were limited by Germany's lack of natural petroleum and dependence on synthetic fuels derived from coal via the Fischer-Tropsch process. These synthetic fuels were high in aromatics but lacked the precise volatility and detonation resistance that Allied chemists had achieved through catalytic cracking and alkylation. In short, the Luftwaffe was trapped in a chemical bottleneck. Meanwhile, in the Allied world, octane had become an invisible weapon. American plants could produce not just 100 octane but entire rivers of it, followed by the rarer and more advanced 115-145, and finally, 150 grade blends. The sheer scale was astonishing. By 1944, the U.S. was refining nearly 1 billion gallons of aviation gasoline per year, a figure unmatched in history. This tidal wave of high-performance fuel didn't just power planes, it powered strategy itself. With 150-grade fuel, P-51 Mustangs could climb faster, cruise farther, and fight longer. Their Rolls-Royce Merlin engines, license-built by Packard in Detroit, were already mechanical masterpieces, but with this new fuel, they reached a new level of performance. At 67 inches of mercury manifold pressure, the Mustang's Merlin could generate well over 1,700 horsepower, enough to chase down Messerschmitt Bf-109s at high altitude or dive at incredible speed without detonating the fuel-air mixture. At 72 inches, the margin of safety was razor-thin, but the payoff was unmatched acceleration and climb. The result was not simply that Allied fighters became superior, it was that they became omnipresent. Long-range escort missions deep into Germany, once impossible, now became routine. Bomber formations that had once suffered catastrophic losses in 1943 could now strike Berlin, Munich, and even the synthetic fuel plants at Luna and Politz with confidence. The hunter had become the hunted. And yet, few outside of engineering circles ever understood why. Pilots noticed the difference immediately. Planes felt stronger. Engines pulled harder. But the invisible alchemy behind that feeling remained the domain of a few chemical engineers and refinery managers scattered across Britain and America. In wartime speeches, generals and politicians praised our brave airmen, but rarely mentioned the anonymous scientists working in places like Baton Rouge, Louisiana, or Stanlow, Cheshire. Yet these were the real alchemists of the 20th century, conjuring from crude oil the energy density that would rewrite the laws of aerial warfare. To the layman, 150-grade fuel was just another technical detail. To a pilot, it was life and death. When the first shipments of purple-dyed 150-grade arrived in the UK in late 1944, RAF test pilots reported extraordinary gains. Tempest Versus could now climb 1,000 feet higher. Spitfire MKX-50s could sustain emergency boosts longer without detonation, and even aging Typhoons found a new lease on life. But as performance rose, so did risk. Engines that once operated safely at 18 pounds of boost were suddenly being pushed to 25 or even 27. The line between engineering triumph and mechanical failure grew thinner with each sortie. One pilot described the experience as flying a thunderstorm. The roar of the supercharger, the vibration of the airframe, the smell of rich fuel mixture, it was intoxicating and terrifying all at once. This was the essence of the chemical crucible, a fusion of bravery and chemistry, of industrial scale and individual courage. Back in the United States, the production miracle behind it all was unfolding quietly but relentlessly. Refineries in Texas, California, and the Midwest had been completely retooled under emergency wartime orders. New catalytic cracking units were installed to convert heavier hydrocarbons into high-octane gasoline components. The alkylation process, still a laboratory curiosity before the war, became a national industry. At the heart of it was isooctane, the gold standard molecule of high-performance aviation fuel. Chemically stable, resistant to premature detonation, and capable of smooth combustion even under extreme compression, it became the key ingredient of 150-grade blends. To produce it in quantity required massive amounts of isobutane and olefins, both in short supply. But necessity drove innovation. Engineers at Standard Oil, Shell, and Phillips developed continuous flow reactors capable of producing thousands of gallons per day. The process was volatile, dangerous, and often experimental. Accidents were common, but the work pressed on. Each gallon of 150-grade fuel represented a chain of decisions, risks, and experiments stretching across the industrial landscape, from the chemical plants of Baton Rouge to the refineries of the Gulf Coast and the airfields of East Anglia. And all of it was orchestrated in near-total secrecy. The British Air Ministry, wary of German intelligence, classified all documentation on 150-grade fuel, and referred to it in code as super high test. Even within the RAF, only senior maintenance officers and squadron leaders knew exactly what it was. Crews simply called it the purple stuff, after the distinctive dye that identified it in storage drums. To most pilots, it was a rumor, a whisper passed along during briefings. You'll get purple fuel next week. Treat her gently until you feel the pull. By early 1945, purple fuel had spread across the 8th Air Force's bases in England. Fighter groups transitioning to it reported noticeable changes in engine response, though they were warned to avoid overboosting until maintenance crews recalibrated carburetors and superchargers. The gains were undeniable. Escort ranges increased by nearly 10%. Time to climb dropped by nearly a minute in some aircraft types. For bomber crews who had endured the brutal attrition of 1943, that meant survival. The Allied air offensive entered its final, devastating phase. German fuel plants were bombed again and again, each time rising from the ashes only to be struck once more. By March 1945, the Reich's synthetic fuel output had collapsed to less than 5% of its 1943 levels. Luftwaffe sorties dwindled, not because of lack of aircraft or pilots, but because there was simply nothing left to burn. The great irony of the air war was that victory was decided less by speed or firepower and more by octane. By April 1945, Allied air supremacy over Europe was absolute. The skies that had once echoed with duels between Spitfires and Messerschmitts were now highways of unchallenged bombers and escorts. Germany's once mighty Luftwaffe, bled dry of fuel, pilots, and hope, could only watch helplessly as the war it had begun burned itself out from above. The final irony was cruel. The German engineers who had built the world's finest piston engines, precision-crafted masterpieces of metallurgy, were now powerless against a chemical reality they could neither match nor mass-produce. Their synthetic fuel plants, bombed to rubble, stood as monuments to a failed industrial strategy, technical genius without industrial depth. Across the Channel, the situation was the reverse. The Allies had turned industry into strategy, chemistry into air power. What had begun as a quiet scientific pursuit in the 1930s had evolved into one of the most decisive industrial efforts of the 20th century. The war in Europe was not just won in the skies over Normandy or Berlin, it was won in refineries and laboratories, in the minds of chemical engineers who understood that in modern warfare, the laws of physics and chemistry could be more decisive than tactics or bravery. When peace finally returned, the story of 150-grade fuel almost disappeared into classified archives and technical manuals. Newspapers celebrated the pilots, the planes, and the generals, but few mentioned the refineries that had produced a substance so advanced that even a decade later, few civilian engines could safely use it. To understand what made grade 150 so extraordinary, one must look beyond its octane number. In aviation terms, octane was shorthand for a fuel's resistance to detonation, the uncontrolled explosion of the fuel-air mixture under pressure. In a piston aircraft engine, detonation was catastrophic. It shattered pistons, cracked cylinder heads, and destroyed crankshafts. The higher the octane rating, the more compression and boost an engine could handle before detonation occurred. But grade 150 didn't just push the boundary, it redefined it. At its core was a cocktail of hydrocarbons blended with tetraethyl lead and a complex mix of aromatic and paraffinic components. Its precise formulation was a state secret, but the result was a fuel that could tolerate boost pressures that had previously been unthinkable. In a typical Merlin engine, for example, normal combat boost was around 18 pounds. With 150-grade fuel, it could safely operate at 25 pounds or even 27 in emergency use, producing bursts of power that could mean the difference between life and death in aerial combat. For American P-51 pilots escorting bombers deep into Germany, this meant they could dive, climb, and dogfight at altitudes and engine settings previously impossible. It wasn't just about horsepower, it was about endurance, flexibility, and confidence. The same story unfolded in the Pacific. The 150-grade fuel saw its greatest use in Europe. The broader lesson, that chemistry could change strategy, carried over into the war against Japan. The massive oil refineries that had been built to supply the European theater now shifted to supporting the Pacific offensive, fueling everything from B-29s to carrier aircraft. By the time Japan surrendered, the United States had constructed the largest and most advanced refining network in history, an infrastructure that would go on to fuel the post-war economic boom, the jet age, and eventually the global transportation system we know today. In that sense, the legacy of 150-grade fuel was not confined to World War II. It became the foundation for post-war aviation science. When jet engines replaced pistons, many assumed that aviation fuel chemistry would fade in importance. In truth, the opposite happened. The techniques pioneered for high-octane gasoline, catalytic cracking, alkylation, polymerization, evolved directly into the jet fuel and petrochemical industries of the Cold War era. The engineers who had learned to manipulate hydrocarbons for piston aircraft now found themselves designing fuels for supersonic jets, rockets, and nuclear submarines. The same scientific mindset, precision chemistry in service of power and performance, became a defining feature of modern industrial civilization. In the years immediately following the war, Allied scientists studied the ruins of German industry and found something telling. While the Germans had excelled in engine design, they had lagged behind in fuel chemistry. Their synthetic fuel program, though ambitious, could never match the energy density and consistency of petroleum-based aviation fuel. The Allies, by contrast, had achieved a synthesis of both: brilliant engines and superior fuel, mass-produced through an industrial base that could adapt faster than any in history. This combination, science, scale, and speed, became the model for the modern military-industrial complex. It demonstrated that wars in the industrial age would no longer be won by tactics alone, but by the total mobilization of intellectual and material resources. In that sense, the chemical crucible was more than a wartime episode. It was a turning point in human history. It marked the moment when the balance of power shifted from mechanical ingenuity to chemical mastery, from individual machines to vast networks of production, research, and logistics. And behind every gallon of that purple-dyed fuel lay a story of invisible heroism. Thousands of chemists, engineers, and refinery workers, men and women alike, labored under wartime secrecy, often unaware of how their work fitted into the larger picture. Some toiled 16-hour shifts in refineries lit by floodlights, others in university laboratories racing to refine a more stable blend. They didn't wear uniforms or medals, but their contributions were every bit as decisive as those who flew Spitfires or Mustangs over Europe. When the war ended, many of these unsung figures quietly returned to civilian life, their wartime achievements unheralded. But the results of their labor endured, in the jetliners that would later cross the Atlantic, in the cars that filled post-war highways, and in the scientific foundations of modern energy technology. The Cold War that followed would see new races, for missiles, for space, for nuclear power, but all were built upon the same industrial and scientific principles forged in the crucible of World War II. The story of 150-grade fuel reminds us that progress is rarely dramatic or visible. It's not always about inventions that explode onto the stage of history. Sometimes it's about the slow, deliberate refinement of an idea, the precise alignment of molecules in a beaker, the steady hum of a refinery unit, the invisible brilliance of chemistry shaping the fate of nations. When we look back on the great engines of that era, the Merlin, the R-2800, the Griffin, we see mechanical marvels. But hidden behind them is something more profound, a testament to human ingenuity at the molecular level. The final victories of the air war were not simply fought in the clouds. They were distilled in laboratories and refined in steel towers rising from the plains of America and Britain. Each droplet of that high-octane fuel carried within it the effort of millions, miners, chemists, machinists, and pilots, all united by a single purpose. In the end, the chemical crucible was not just a chapter of World War II. It was the story of how humanity learned to command the elements themselves, and in doing so, reshaped the modern world.